Yes, so it's recording in progress. So let's get started. And so first of all, on behalf of the UTexas and Portland State University and Arizona State Universities, welcome to the UTexas Field Nonlinear Cyclic Shear Measurement in Soil Workshop. So those who are may not familiar with the NHERI facility. So NHERI stands for the Natural Hazard Engineering Research Infrastructures, and I will show more like other facilities, but we are the one of the facility called Large Mobile Shaker Facility. And the NERI is funded by National Science Foundation to advancing innovation and research, particularly for the natural hazard engineering. So we are privileged to help the NSF awardees and make their like research become real. So here's the agenda for today. So we will have a welcome, introduction, and overview of the workshop goal from 1 to 1:30. And after that, I will talk about the capability of the UTexas facilities. And the following of the introductions, Dr. Kevin will present about the geotechnical mitigation of earthquake-induced soil liquefactions. And we'll have a coffee break, like everybody's favorite. And Diane and Arash may talk about the field trials of MID for liquefaction mitigation, implementation, longevity, and retreatment. And I will continue to do the presentation on the field nonlinear cycling measurement using the helical power testing method. Arash will compare the last year data between field and lab. He will compare the results. And the last presentation, I will talk about the NSF proposal for the planning, budgeting, and data sharing. So he will talk about the chairpersons and members of organized committee. Without them, the workshop wasn't possible. So the chair is Dr. Kenneth Stokey. He's the PI of our Texas facilities. And the co-chair is Dr. Edward Kawazenji, Director of the Center for the Bio-Mediated and Bio-Inspired Geotechniques, professor at Arizona State University. Co-chair, Raj, sorry for the last name. How you pronounce it?
First time that this happens.
Okay. Yeah. All right. So associate professor at the Portland State Universities and committee member, Diane Mo, assistant professor at the Portland State University. So, and I'm the last one. I'm the UTexas operation manager. So here's just a small percentage showing the workshop participate by the affiliation. So we have 42% from the faculty, 35% from student, and 30% for the industry. So we have like kind of like even number that we need for this workshop. The goal of this workshop is first to showcase the UTexas capability of measuring cycling nonlinear soil behavior at depth. So we have a new testing technique, like we'll improve from the conventional way of doing liquefaction, by measuring the nonlinear at depth. So we'll try to showcase that. At the same time, highlight the biogeotechnical mitigation of soil liquefaction, including the microbial-induced desaturation method. Every workshop will try to bring like together researcher, practitioners, and students to advancing the understanding of soil behavior under dynamic loadings. But for us, we are in the field testing like facility, so emphasize on the field testing method. So we hope we can like have more collaborations and share practical experience and inspire a new approach to challenge in geotechnical earthquake engineering. And we hope that we can help the assistant professor and the professors that we can write the proposal with us for the NSF. And we also have some insight for the practitioners for the student that we can also like have new ideas for to overcome some of the challenges. Okay, sorry, that was accident. Go to screen.
Yeah. Oh, so I wanted to be connected, but it says it's scheduled for tomorrow.
So those are the first email that I sent. So those are I sent you the email with saying update important updates because those are did you have I think you will receive the second email, isn't it? And then they have a new link. So you have to use that link. Yes, it's here. So I will talk about the NHERI UTexas facilities and show the capability of our facility. So our site is called Large Mobile Shaker Facility. So we own five volts, large 5 volts. So that generate the vibration on the ground. So we have the associate with instruments such as accelerometer, geophones, and sometimes power pressure transducers. We'll install it in the ground or sometime at the surface. And we record the waveforms and try to do like fun things. So we can do 2D and 3D like imagings, and we also can do the liquefaction testings or soil structure interactions. Here's our PI of our facility, Kenneth Stokey. There's three co-PI, Dr. Cox, Patricia Clayton, and Dr. Gilbert. And here's me. I am the all-person manager at UTexas facility. So NHERI stands for Natural Engineering Research Infrastructure. There are 7 experimental facilities with the large-scale equipment. We have the Lehigh University, large-scale multi-directional hybrid simulation device. University of Florida, the boundary layer wind tunnels. Florida International University, wind simulations. UC San Diego have the large high-performance outdoor shaker tables. UC Davis have the centrifuge, and here's us. We are the mobile shaker facility. And the Oregon State University is not from here. They have the large wave looms and directional wave basin. Well, there's one sizable infrastructure facility of archiving sharing data. So every NSF award we help, we upload the data to the center called Design Sec. It's also located inside the University of Texas. I will talk more about the archiving and sharing data in the later slide. There's one computational method and simulation center called SIM Center. This is like multi-university group, but their headquarters in the UC Berkeley. One post-disaster rapid response facility called RAPID is located in the University of Washington, and there's one network coordinated office called NCO is located in Purdue. So those are the structures of the NHERI. So now I'll focus on our facility. Let's go with our line of our presentation. I'll talk about the shaker instrumentation, what we have, and I'll particularly talk more about the distributed accuracy sensing interrogator. Those are like a cutting edge technology that we recently use a lot, and there's a lot of like requests about renting this device. And we'll talk about our science plan, the research area of interest. So we have 2D, 3D subsurface imagings, in situ nonlinear testing, and the soil structure interaction. And I will show the example project for each our research area of interest. So we own 5 shakers. So there's the 5, but I will mostly highlight in the first 3. So those are used a lot for the research and for the non-research projects. First, the shaker is called T-Rex. It can shake in 3 directions: vertical, inline, and transverse. And that shaking orientation will be just changed by simply pushing a button. So it is really unique. And I think this is the only one really operating in the world. And here's our liquidator. We have the lowest frequency shaker that can generate down to 0.3 hertz, and with a special configuration, we can generate down to like 0.7 hertz. Here's a sample. I think you will see T-Rex tomorrow at the field demonstrations. They're in the Portland right now. The thumper is we call urban shaker because that's the only truck that legally drive on the road because the the shaking mechanism is mounted on the commercial truck. And here's two mid-size, the Raptor and Rattlers, and we also have called Big Rig that can transport our big shakers to the site. And we only operate the Big Rig inside the Texas state because outside outside the state they have all different rules and the permittings, and that is really hard for us to get in time. So we use the external like trucking company to deliver our vibrosis for the outside of Texas. So we also have the field supply trucks and instrument vans. So if you want to know more, there's a Design Safe, the UTexas Design Safe homepage. There's every details is there. And another option, what you can do is you can go to YouTube and search for T-Rex. We have a YouTube film with Tom Scott, and we have like 1.6 million views on it. So if you have time, just try to go to YouTube and search the T-Rex. Well, yeah, you have to search T-Rex and like fibrosis. If you just search T-Rex and they're only the like dinosaurs, you have to scroll down quite a bit. So like T-Rex and like fibrosis or truck. So why we need different truck? Why we just have one? Because they have different frequency range and output. So this is a vertical shaking. And so one thing. So the liquidator and also thumper can change to the different direction of the shaking. For the liquidator, it takes 4 whole 2 days in a special like equipment. So it is really hard to do in the field. For the thumper, like 4 or 5 hours in the field. So they still have the possibility, it's not recommended. So vertical force, the T-Rex is the frequency they can generate to 12 to like 100 hertz with like 60,000 pounds. And the Raptor and it's in between our mid-size shaker. The liquidator can shake down to the 1.3, and I will show you some of the shakings. And with a special configuration, we can go down to 0.7 hertz. So we use this nonlinear liquefaction cyclic measurement testing using the thumper because thumper can go to 17 hertz to up to 200 hertz. We need really high frequency to measure the Gmax. And this is the horizontal force output is similar, but we have the T-Rex and the Rattlers is similar, and the thumper it also have the possibilities of changing directions. So I will show you one of the horizontal shaking. So this is the highest amplitude shaking in the horizontal mode because here's the T-Rex. We have a Rattler outside. We sync those together with have the same like motions to create the larger displacement, larger amplitude. So you see like the wooden pad is like moving, like jumping around. And I think this is the biggest shaking that we have. Yes, it feels like an earthquake. So tomorrow the T-Rex is on site. We'll do some shaking, but it will be not close to this amplitude. I don't want to get warning from the Oregon State about there's a levee there. So I don't want to get any warning from them. Okay, so this is the liquidators, the standard configuration. I think it would be like 2 hertz shaking. The mass is moving back and forth. Generate the wave. We have the base plate on the ground, so that generates the wave transmitting to the ground. Oh, it's not amusing. So this is a special configuration we call push-up. Okay, so no, it's not funny. It takes a long time to make this happen. And now we have like larger mass moving like up and down. That's the only we can generate the 0.7 hertz. We measure like a mile wavelengths, and then we can I remember like 1,000 feet shear velocity profile using this special configuration. And the manufacturers say, don't do that. But like, yeah, we did it. So I'll show you our vibrosis, generate the waves and vibrate. So I'll show you the sensors when we record those signals. We have 110 100 geophones, and recent inventory shows like we only have 70, and we have 200 4.5 geophones and 20 like trillium complex and broadband seismometer. And these two are kind of recently purchased that we purchased in 2021. We have 100 smart photo, 3 component, fiber geophone, GPS synced. So video this sensor is that is run by battery packs and GPS sync. So you installed at the location where you want, you shape at a various location for your testing for like a month, and then you just pick it up and you can download the data. Just one thing that you have to make sure is like you have to know where you trigger the signal. So if not, there's gonna be just a bunch of record that you can never really figure out. To the right side is the OptaSense fiber optic distributed acoustic sensing interrogator. So this is a DAS IU. So DAS use the fiber optic cable to measure the strain rate. So there will be the fiber optic cable will be buried to the ground and hook up to our OptaSense IU. And this IU sends a laser pulse. And when that laser is sensing any kind of imperfection, they backscatter. And this IU analyze the backscatter like light and calculate the frequency and the strain rate. And why this is useful? Because it's have really high resolution. So our DAS interrogator have the 1 meter channel separation. That means, let's say we have like 1,000 meter cables, and at each 1 meter, we can get a measurement. So it'll be equivalent to have like 1,000 geophone along the arrays. So let's think about like the IU is expensive, but the fiber optic cable for like kilometer to kilometer is like $2,000, $3,000. The one geophone costs like $200, and then we have 1,000, or it will cost $200,000. So it is really cost effective. But what one question arises, okay, those are not really like a strain rate, not the strain or like a velocity we measure. Is that useful for the earthquake engineering applications? So we have the 2021 DAS workshop. We have the T-Rex, we have the cable line, and we hook up to the DAS interrogator. And we have 2 meter geophone spacing, 48 verticals and 48 horizontals. And we compare the data. It helped by Peter Hubbard. He have the publication that how to change the strain rate to the strain and to the velocity. So here's the comparison. I don't know if you guys can really see details. So this like kind of yellow is the geophones, and these blue and red is show the DAS record. So it's not exactly the same, but once you produce like analyze the data, collect the data for the full wave emergence, like MSW, SSW, all kind of other like earthquake engineering applications, they will give you like almost like similar answers. So please go to this like that workshop like videos that we posted in the Design Safe, and also Peter Hubbard's publication. It will show you how to use those data. We also publish this data set, every data set to the Design Safe. This is to location. So we asked a lot of researchers to go to the Design Safe data depot. There's tons of data there. So for this the Hornsby Bend side, we have a DAS, we have a down roll, cross roll, MSW, SSW. So we know the Hornsby Bend side, we have the reference shear velocity profile there. If you want to use the DAS data, try to do like another like full wave inversion or like other kind of analysis to try to have like 2D like profiles. Here's the data you need. So just go there and try to download, and please use it, because we have the University of Mississippi actually used this the published data set and done the diffraction analysis, find the CPG locations. So now, but this was not data was not tailored to their like diffraction analysis. But once they run some kind of proof of concept analysis and they find the CPG where it's supposed to be, they reach out to us a few months ago. He wanted to do like additional like testing with us, and they get funded. So we'll have another testing just tailored to their diffraction analysis. Maybe we'll have our thumper or the shakers closer to the DAS, and then they want to have more shot points. So please go, and there's like not just for DAS, any kind of like there's a lot of tons of data that it will be useful and inspiring research. Other than the experimental facility, we are mobile shakers. We can go all around the United States, even for overseas. So that's almost like NEES and NHERI. So for like 20 years, we've done like 50 NSF projects and 50 non-NSF projects, including Taiwan, we went to Hawaii, and we also went to New Zealand. Well, I'll show you the New Zealand examples in the later talk about the nonlinear cycling measurements. And here's some animation of our UTexas science plan. So it is the 2D and 3D imaging. It is just a conceptual. So we have the geophones and tied to the roses move, and then sending the waves, and then run the full wave and analysis, try to find the buoys. And this is I will call like conventional method of our liquefaction testing. So the shaking was happening in the surface, and our embedded sensors in the ground try to measure the nonlinearity of the soil. And this is the soil structure interaction examples. Like we really shake the bridge. We have the project with Rutgers University to shake one of the bridge in Hamilton, and we compare our actual field data with the numerical analysis. So now I will give you some of the projects that we have worked before in our research of area interest. So that's going to be more application to the earthquake engineering, digital earthquake engineering part, 3D seismic waveform and topography. So done with the University of Florida, Dr. Tran, and then Dr. Cox from the UTexas University. So this site is called Newberry site, is known for the cavity and subsurface anomalies. We placed 48 geophones, and we shake a thumper at 65 different locations, run the full wave emergence, and then we got this 2D Shear velocity profile. And we think they're going to be very corresponding to the low Shear velocity. They're going to be the sinkholes. So we check with SPT M values, and they find the void. And then, yes, it was kind of one of the successful 2D profile imaging projects. Now, this is more like earth science part of the 2D, 3D imagings. So we have collaborated with USGS and University of Miami and tried to image the three-dimensional structures and magma system beneath the summit of Kilauea volcano. USGS deployed 1,800 sensors around the Kilauea volcano. It takes like 3 or 4 weeks, and they use helicopter to deliver the sensor to the location, and people like climb up and place the geophones or their sensors. The longest wave that they made, we shake at 400 locations around the Kilauea volcano. So the longest wave that they measure, this is from the 7 kilo offset from the geophone. They measure our P and S wave. That is really great. So the USGS will use this extensive data to create the CT images like CT scan. They want to get the cross section of the Kilauea volcano. So it will show how the Kilauea volcano store the magma, how they transfer magma to one to another locations. And that's going to be like give you a scientific like knowledge that how the Kilauea eruption mechanism and valuable information. But it'll be really good for the policymaker, or emergency or learning system to make our community like safer. And the second area is intrinsic factor testing is also like nonlinear, like story measurement. And we did it for Dr. Cav's engine and Arash. So we prove, or they have the method called the microbial induced desaturation. So they desaturate the pad, we do the crossflow testing and prove there is a desaturated zones. And we have, and this is more about my next talk. So we have some limitation in the shaker shaking at the surface, the vibrate at the surface that limits some of the nonlinear measurement. So we have the pile called the helical pile. We install the helical pile at the depth of interest. We at the same depth we install the geophones, the PPTs. We shake the thumper on the top of the helical pile. We transmit the energy, the vibration through the helical piles, and we will have the horizontally propagating wave at the single layer with the same confined pressure, and then we can have better like nonlinear measurements. The left side is the project we done in Hawaii, and the right side is kind of a little bit spoiler alert, but this is the measurement that we have made. We also do the soil foundation interaction. So this was the project with Dr. Mo in the University of Houston. So this the aim of this research offers to develop a periodic barrier capability of effectively attenuating income sizing waves. So using that barrier, they can tune the waveform to a certain frequency that can mitigate the damage from the existing earthquake. And it was really helpful. So there's a lot of publication from this. And so it's officially early, but so if you have any questions, just please contact me. So here's my emails. And thank you all the support for the National Science Foundations. And actually this year is the 75 years NSF and anniversaries. But I know they going through a lot of hard time, but thank you and because your support from them. Yes. So I finished a little early, so I will give more time to Dr. Cav's engine for his presentation.
Oh.
Thank you. Now I cannot find. I put this. Oh, yes. Oh, Shear. Yes.
All right. Well, good afternoon, everybody. It's nice to be here. Nice to be back in Portland. And I say back in Portland because in preparing for this presentation, I look back at, we had another workshop like this several years ago. I didn't remember exactly how many, but I knew I'd made a presentation. And so I went to pull up the introduction to that presentation, and I noticed that it's been exactly 6 years. September 11th. In fact, I thought it was a mistake. I was going to just modify this slide as the introduction slide for my presentation. And so first thing I did is I went to modify the date, and I thought, wait a minute, it is September 11th, you know? It set me back a little bit, though. It's hard to think that it's been 6 years since we had our first workshop on this project, or that's associated with this project. So thought I'd start with a little bit of a definition of what we mean by biogeotechnical engineering. And 10 years ago, 10 and a half years ago, the National Science Foundation funded an engineering research center at Arizona State University on this emerging field of biogeotechnical engineering. And ASU is in the lead, but we were collaborating with UC Davis, Georgia Tech, and New Mexico State. If you're not familiar with the Engineering Research Center program, you're funded for 10 years. So we had 10 years of good funding. July 31 was the end. So I'm now dealing with my hangover from 10 years of consistent funding. But when we talk about biogeotechnical engineering, we talk about two somewhat distinct but related processes, biomediated processes that are subsurface processes that are controlled, managed and controlled through biological activity, usually microbiological activity since we're below ground, but living organisms. And then bio-inspired processes where we use biological principles to apply new abiotic solutions. And in fact, we started looking at this technique, microbially induced desaturation, as a biomediated process, but in fact, there's some bio-inspiration involved, and I will talk about that. So the premise in this field is that nature has developed many elegant biogeotechnical processes, basically through billions of years of trial and error. If you want to look at a slope that's going to be stable over for a long period of time, go look at slopes in nature that have been stable over long periods of time, understand why they've been able to survive, and then learn how to reproduce that. So these biogeotechnical processes address many important geotechnical problems. We can learn from nature how to address those problems like erosion or liquefaction and other problems too that maybe weren't directly addressed by these processes, but that these processes can address. So some examples of biomediated processes are shown on this slide. In the upper left are the White Cliffs of Dover. These are carbonate precipitated. This is carbonate precipitation. And so, sure, from a geologic perspective, these slopes are, quote, unstable, they're erodible. But from an engineering perspective, if you look at a 75 to 100-year lifespan, they're remarkably stable. On the upper right is a mangrove tree, mangrove tree, I guess mangrove tree, and the lateral resistance supplied by the root system of this tree is an order of magnitude more efficient than the lateral support systems that we use in engineering practice. So what can we learn from the mangrove tree to enhance the lateral resistance of our foundations? On the bottom and in the middle are a couple of analogs that we can look at in terms of being efficient in penetrating the soil and safe in tunneling through the soil. On the left-hand side is a root that's germinated, a seed that's germinated. You see the root system, it's shot out into the soil to provide remarkable support, but also that plumule that pops up out of the soil by breaking out the soil cover does so with remarkable efficiency. So what can we learn from that? What can we learn? How to penetrate the soil efficiently, like the root system, how to break out on top of soil cover, like the plumule. The right-hand side is an ant farm, and this says Carlos Santa Marina, but I think that one came from David Frost. But anyway, you know, some of you may have had ant farms like that when you were growing up. And if you watch them, you find that the ants that tunnel incredibly safely. These tunnels almost never collapse, and yet it's a granular material. It's like blocky rock. We have lots of problems with tunneling and blocky rock with the blocks caving in on us. So what does the ant know that we don't know? And according to David, who takes slow motion pictures of this, the lead ant goes up to the head of the tunnel and he actually taps on the sand grains with his, I don't know, proboscis or whatever it is. And there's some signal that tell them if they can safely remove that sand grain without the tunnel collapsing. So what is that signal? How can we use that for geotechnical purposes? They're also remarkably efficient. And Carlos says that if you look at the amount of energy they use to remove one unit volume of soil, it's 2 orders of magnitude more efficient than our tunneling. So again, what can we learn from ants to be more efficient? And then in the middle, I just threw that in there because that's Bill Murray's buddy from Caddyshack. But in fact, moles communicate with each other wirelessly on the ground. And Julian Tao at ASU is developing wireless underground communication systems by emulating how the moles communicate in the ground. They do it 2 different ways, but the one I find interesting is it's called drumming. They drum their head on the side of the tunnel, and that sends out a signal to other moles in the ground to let them know, hey, I'm here, stay away, you know. So some examples of how we can learn from nature. So if we look at the different biogeotechnical mechanisms of ground improvement, the 2 I'm going to talk about today are mineral precipitation, specifically carbonate precipitation and desaturation, But we also have biofilms, biopolymers, root-inspired reinforcement foundations, and self-motile or burrowing probes. And they all have processes that they've developed through evolution that we can learn from and use to our advantage. So, as I mentioned in the beginning, today I'm going to talk a little bit about carbonate precipitation, because that's what led us to using desaturation as a mitigation mechanism for liquefaction. Not that you couldn't use carbonate precipitation, but today we're talking about desaturation. So, calcium carbonate precipitation, calcite, one of the most common minerals in nature, maybe the only one that's more common is salt. In terms of biogeotechnical engineering, which has really exploded in the last 10 years as a field of study, it's the most studied process. There are labs all over the world looking at MICP, microbially induced carbonate precipitation. And in fact, when I got involved with it, I told my students, I don't want to do MICP. Everybody's doing MICP. Let's look for some other processes that we can study. But why are all these people studying carbonate precipitation? Because it's very effective at increasing the strength, the stiffness, and the dilatancy of the soil. And so if you can do it cost effectively, it has a lot of geotechnical applications. And when we look at calcium carbonate precipitation mechanisms to try and learn from them, there are many. My first PhD student looked at this, identified 7 different carbonate precipitation processes in nature. But there are more than 7, because he was just looking at the nature-inspired ones, but there are some anthropogenic ones too. For instance, the white scale that develops around your hose bib, that's carbonate precipitation. What we learned, though, is that some of them, besides precipitating carbonate, generate biogas. And that's what led us to what we're going to talk about today, which is microbially induced desaturation. And if we can effectively control carbonate precipitation, if we can get that to happen where we, instead of around a hose bib or instead of clogging a well screen, if we can get that to happen in the soil pores, then it has tremendous amount of applications. Liquefaction mitigation, enhancing bearing capacity, stabilizing tunnels and excavations, stabilizing slopes. One of the most fruitful for us in terms of raising money has been fugitive dust control. You know, you go to a construction site, Arizona, it's 110 degrees and it's 15% relative humidity. And there's a guy there with a hose who's there for 10 hours spraying water to suppress the dust so they don't get fined. Well, we have a carbonate precipitation solution. Apply it once and you're done, one and done. Sustainable, cost effective. We just got $800,000 from the Department of Defense to look at dust control in Yuma, at the Yuma Proving Grounds. And then biobricks, making building materials by precipitating carbonate to bind aggregate together. You know, when there are 1.3 billion concrete blocks manufactured in the US every year using Portland cement. That's a billion. If I can get 1% of that market and charge 10 cents a block, I'll be able to retire with Professor Stokey, you know? All right, so mitigation of liquefaction. If we look at liquefaction, and we look at the techniques for mitigation of liquefaction, they're all limited in terms of applying them under and around existing facilities. You know, densification by vibration and cavity expansion, it's going to be disruptive to an existing facility. Drainage, installing sand drains or wick drains, that'll be accompanied by settlement. It'll be accompanied by expelling a lot of water when the ground liquefies. Stabilizing the soil by soil mixing. It's hard to do that under a building. It's going to be very disruptive. Reinforcement with stone columns or other reinforcement elements. Again, you're not going to do that beneath an existing building. Grouting, penetration grouting and compaction grouting has limited applicability and it's very expensive. So basically, there's really no cost-effective method for mitigation of liquefaction under existing facilities. So the advantage that biogeotechnical liquefaction mitigation has is it's non-disruptive. It's not non-intrusive. I still got to drill holes, but depending on what technique I use, I'm going to pump a treatment solution through those into those holes. And so we can do that non-disruptively under existing and around existing facilities. And so that's really stoked our interest. I'll show you why in a minute. And we started looking at 3 different biogeotechnologies. I mentioned microbially induced carbonate precipitation. I wasn't interested in that, but Leon von Passen, who came and joined us at ASU, is one of the experts on MICP. Enzyme-induced carbonate precipitation. That was our take on MICP. In MICP, you grow microbes in the ground. Well, you can grow them out of the ground and inject them into the ground, but it's more efficient to stimulate natural microbes in the ground. And the microbes you want to stimulate are ureolytic microbes. They have an enzyme called urease in their structure. Okay, but you can get urease enzyme, you can buy it in lab supply, or you can make it yourself out of soybeans or a relative of the soybean called the jack bean. You don't have to worry about stimulating it. All of the carbon goes into creating carbonate, which is what you want to do. It doesn't have to feed the microbes. And it has less pore size limitations. Microbes are kind of a little chunkier like me than you might think. It's hard for them to fit through the pores of fine-grained soils like the silt that we're going to, the low plasticity silt that we're going to, at the site we're going to tomorrow. The basic enzyme unit is 12 nanometers. Usually there are packets of them, several in a packet, but still the enzyme can penetrate fine-grained soils. It's a little bit limited by hydraulic conductivity, how fast you can get it in there, but it can penetrate finer soils. And then microbially induced desaturation and precipitation, MIDP. Notice the P there. That's a little different. We're just talking about MID today. You'll see why in a minute. But via a process called denitrification. And I'll talk about that in a second. Why do we care? So, I lived in Southern California for 20 years as a practicing geotechnical engineer. Liquefaction was great for business. This is the Pacific Coast Highway in Newport Beach. And that's what it looks like today. And none of these structures were designed with any consideration of liquefaction. This is the same exact area, Pacific Coast Highway in Newport Beach, in the 1933 Long Beach earthquake. And the 1933 Long Beach earthquake wasn't in Long Beach. The epicenter was in Newport Beach. And look at the lateral spreading and cracking. We see that very characteristic of liquefaction in earthquakes. And that's the land that all these homes are built on. And the garage of a 3-bedroom home is worth $1 million in Newport Beach. So a repeat of the 1933 earthquake would probably cost something like $10 to $15 billion in property damage. And how do we mitigate that? Well, hopefully biogeotechnically. So liquefaction mitigation via MIDP, sometimes we just call it denitrification, relies on reduction of nitrogen in the soil. So we put nitrite in the soil, nitrate. Natural bacteria reduce that to nitrite and then to nitrogen and carbon dioxide. And both of those products work for us. The nitrogen is insoluble. So it remains in the soil as bubbles, little bubbles in the pores, unless you create so much that you fracture the soil in the vents. So you have to be a little careful. The carbon dioxide is soluble. So the carbon dioxide goes into the water and becomes carbonate. It grabs another oxygen and becomes CO3 carbonate. If you have calcite available, they'll get together and create calcium carbonate. And then in the right situation, they'll precipitate. The microbes that do this denitrification are, in the words of my microbiological colleagues, ubiquitous. I became a geotechnical engineer because I didn't want to take biology and chemistry. And I find myself 50 years later talking about facultative anaerobes. And so, you're always learning, right? But in fact, it's widely used in water treatment for reducing nitrates and nitrites from the soil. So they're everywhere and very easy to stimulate. You do need to add some nutrients for them and a calcium source. So something like calcium acetate, which will provide nutrients for the microbes, and then a calcium ion to create the carbonate we add to the soil. And when we started looking at this with one of my early PhD students, Sean O'Donnell, we said, well, when we first started, we were just looking at this carbonate precipitation. The dirty little secret about MICP and EICP is that it has a byproduct that's a groundwater contaminant called ammonium chloride. And it produces it in quantities like 10 times greater than what's allowable in drinking water. So that's one of the big issues in using that method in practice. When I first got involved with my first PhD student working on this, I said, let's find another process. And we looked at a couple of them, and we settled on this process because unless you have sulfate in the soil, the byproducts are benign, nitrogen and carbon dioxide. They're non-toxic. So we started using this for carbonate precipitation, and it started, we had a problem because we were generating all this gas. We were venting all this nitrogen gas, which was benign, but it was messing up our columns and our experiments. And then we had this aha moment, wait a minute, that's desaturation, that's a carbonate precipitation mechanism. So, and the gas production happens right away. Within a day, we're producing gas. The difference between this technique and MICP is that the carbonate precipitation is maybe 2 orders of magnitude slower. In MICP, in a week or two, you can generate 5 to 10% carbonate in the soil. In MIDP, it could take 6 months to generate 1% carbonate. So we said, well, okay, but until we generate enough carbonate, and at the time, we thought we needed 5 to 10% carbonate to strengthen the soil based on results with MICP. We'll have desaturation. So it's a two-stage process. Desaturation initially, very rapidly, will provide interim mitigation. And then in the long term, we'll precipitate carbonate and we'll cement the soil together, and we won't have to worry about the desaturation anymore. We have changed our perspective on that a little bit, as you will see. You'll hear from me and from others. So stage one, we did some biotic testing for desaturation. We had columns. We had some solid columns so that we could test them mechanically afterwards. We had some lucite columns. And very rapidly, we started to see voids developing in those lucite columns, big bubbles of nitrogen that would then vent. And the water level in those columns would rise. Why? Because when we generate these nitrogen bubbles, it displaces water from the pores and it pushes it up out of the soil. So very quickly, we had evidence and we learned how to control the desaturation process. The slide in the middle is an estimate of the degree of saturation just based on the amount of water that we vent out of the column. And it says degree of saturation, but it really should be the change in saturation, because we would treat it and then come back the next day and treat it again and come back the next day. And every day we would measure how much water was expelled from the column. And we would use that as a measure of desaturation. If you added all those up, it does make a little sense. It gets down to about 40% saturation. We probably were leveling out at about 70% because we didn't take into account venting of the gas. But anyway, we were able to do biotic testing outside of our testing equipment to demonstrate that we could very quickly desaturate soil. To do it within the testing equipment, we didn't have the setup at that time. We do now, but in the early days of the experiment, we couldn't treat within a cyclic simple shear device, which is my preferred device for the liquefaction, or a cyclic triaxial device. So here's some results. Again, we learned quickly the best way to monitor the degree of saturation was by measuring P waves, as Professor Stokely would tell us. And so here are some results of the monitoring versus P wave up there at about 1100 or 1050 meters per second. That's saturated soil. And very quickly, within a day, we dropped down to 800 meters per second. And then maintain that level of saturation, in this case, for a little over 2 weeks. So again, evidence that we can very quickly desaturate the soil. We also wanted to see what the influence of desaturation was on the cyclic shear strength. For that, we used abiotic testing because, as I mentioned, we weren't set up to treat biotically in the cell. But we learned doing abiotic testing that even a little bit of desaturation significantly increases the cyclic shear strength of the soil. If you can drop the degree of saturation to 97%, you can increase the cyclic shear resistance by 20, 30%, depending on the relative density of the soil. On the right-hand side there, and I know this is Professor Stokely may not like this data very much, but we think we are able, even though degree of saturation is relatively insensitive to P wave velocity between a dry soil and, say, 90% degree saturation, we were able to, we thought, develop correlation as a function of the overburden pressure. I think Dr. Stokely would tell you that these lines, cursor, Well, these lines here should probably come all the way over to here and don't go up till about 99%. But we have lab data, you know, Ken? So then we started precipitating calcium carbonate biologically and measuring the stiffness and the cyclic shear strength. And what we found was that it didn't take very much carbonate to significantly increase the cyclic shear strength. If we look at the cyclic shear strength curve on the left-hand side, Ottawa 2030 sand, relative density of about 40%, and with just 0.5% calcium carbonate, we had a 40% increase in the shear strength. At 1% calcium carbonate, we basically doubled the cyclic shear strength. We did not expect that. We thought it was surprising, but we went to investigate it. And here's why. So, and I love this picture. Sean O'Donnell took this scanning electron microscope picture as part of his research. So this is an SEM photo of some sand that we treated. We got about 1% calcium carbonate. It's been dried and made a thin section so we can take an SEM photo. This is organic matter outlining a bubble, right? Perfect sphere. How else would we get such a nice surface? So this was a nitrogen bubble that desaturated. And the nitrogen bubble, these are the carbonate crystals. The nitrogen bubble pushed the carbonate into the contact zone between the particles. In MICP, the carbonate coats the particle surface and then eventually starts growing together at the contacts. MIDP, the bubbles push the carbonate into the contacts. And so it's a very efficient way to increase the cyclic shear strength of the soil, the granular soils anyway. So we did our lab testing. What were our key findings? That a very small amount of desaturation leads to a significant increase in liquefaction resistance. That P-wave velocity can track saturation. That was through the abiotic experiments. The biotic experiments told us that the desaturation occurs very quickly, that small amounts of calcite precipitation lead to significant increases in shear strength. And our conclusion at this stage was denitrification shows promise for mitigation of liquefaction as a two-stage process. And if you read the O'Donnell et al. Papers, you'll see that that was our conclusion. And then we had what I would call a eureka moment. The eureka moment was, who needs the P? Why do we need the precipitation? We're desaturating the soil. That's a liquefaction mechanism. The desaturation occurs almost instantly. We just need to get one pore volume of treatment solution into the soil. Even 1% calcite precipitation takes months and takes 40 times more substrate. So it's going to be more expensive. It's going to be more time consuming. And there's lab and field data that indicates that desaturation in granular soils may persist for long periods of time. Mishek Yagin in Northeastern was doing work on abiotic precipitation using electrolysis, using the chemicals. I called it the effort-dense solution, you know, like a fizzy chemical that would create gas. Okamura et al. In Japan reported on sand compaction columns that they took using freezing. They took cores of after 15 years, and the bubbles were still there. It was still desaturated. The desaturation that was created on the installation of the columns below the water table had persisted for 15 years. So there's good evidence that desaturation will persist. So let's forget about the P. Why not MID? And even if it only persists for 5 years, I'll just go back and retreat, and I'll still be ahead of the game versus using MICP, and I don't have to worry about that dirty little byproduct of ammonium chloride. So some additional considerations when you think about desaturation. First of all, we know a little bit of desaturation significantly dampens pore pressure. Why else would we spend so much time back pressure saturating samples in the lab, right? You know, a B value of like 0.3. So we try for what? 0.95 for our B values in the lab. A B value of 0.3 is a degree of saturation of about 98%. So a little bit of saturation really dampens pore pressure. If we dampen the pore pressure, we're going to mitigate liquefaction. Yagin and others were investigating abiotic desaturation for liquefaction mitigation. You know, 2011, we had an earthquake in Christchurch, a lot of post-earthquake, a lot of liquefaction, a lot of post-earthquake studies. And many of the studies indicated that the liquefaction always occurred beneath the seasonal low of water table. That in the surface layer where the water table fluctuated seasonally, it wasn't liquefying unless it was due to venting of liquefaction from below. So soils in the water table fluctuation zone were reported not to liquefy, likely due to the unsaturated layer. But here's my bio-inspiration. I thought back and I remembered a presentation by Mike Jamielkowski, very famous geotechnical engineer, for those of you who are too young to know, and on a proposed bridge across the Straits of Messina in Italy. And this was proposed, and I think this project is kind of back on the table. The world's longest suspension bridge, a 3,300 meter span from Sicily to the mainland. And on one shore, there were sand deposits, but they had done laboratory testing that indicated, even though it was a very low relative density, it wouldn't liquefy. And I remember asking Mike about it, and he said, well, that's because the soil wasn't saturated. It was an area of methanogenesis. There was a lot of organic material, and there was methane in the soil that had lowered the degree of saturation to between 90 and 95%. So that's my bio-inspiration, that they were convinced that as long as that methanogenesis persisted, the soil would remain resistant to liquefaction because it was desaturation. All right, so how do we prove it? Well, one of the things we embarked on was a centrifuge testing program. One of my PhD students went up to UC Davis, and we did centrifuge testing to demonstrate mitigation via biogenic desaturation under field stresses. And we had two objectives to the centrifuge program: to investigate biogas generation and retention under field stresses, and then to investigate gas retention during and after shaking. Was the shaking going to vent all the gas, and would we have to retreat after an earthquake? So centrifuge model details. We used the 1 meter centrifuge at UC Davis, their flexible shear beam container. We used F65 silica sand. Until then, all our laboratory experiments have been on Ottawa 2030, has a mean grain size of about 2 millimeters. Silica F60 is 0.2 millimeters, but remember, we were going to accelerate this centrifuge up to about 60 G. So that 0.2 millimeters on the prototype type scale becomes 12 millimeters, or half an inch. And if we had Ottawa 2030 sand, it would have been like testing boulders. We decided to desaturate using augmentation rather than stimulation. So if you want to use the native microbes, you pump the nutrients in that the microbes need, and then you let them grow. That takes time. Augmentation, we mix up a solution ahead of time that has the denitrifiers in it, called a mixed culture of denitrifiers. We enrich it with the food that the microbes like, and we pump that into the soil. And that accelerates the desaturation process. You don't want to tie the arm up on the centrifuge for three weeks while you're waiting for the bugs to grow. So this was the way to accelerate the testing. So this was our model. We had 3 moisture content sensors, the GS3s, yeah. Oh, where'd it go? Well, they're in there somewhere. We had 6 pairs of bender elements. We had 3 pore pressure transducers. I think the GS, and then 3 accelerometers. And we had set the model up so we could do 4 CBT tests. Before and then after a certain amount of treatment, and then after shaking, to see how it affected the CBT resistance. We saturated the sand, then we flushed our treatment solution in, 2 pore volumes of treatment solution in from the bottom. We watched the degree of saturation with the P waves. When the top layer got to a degree of saturation of about 90%, actually I said 60 G, we accelerated it to 80 Gs, monitored the decrease in saturation as we accelerated it, conducted a CPT test, loaded the soil cyclically, left it overnight to let some more gas generate, and then repeated the cyclic loading and the cone penetrometer test. So the first set of shaking, we had 9 shakes of 15 uniform cycles per shake, representative magnitude 7.5 earthquake. The PGA started at 0.05 G, and then we increased it incrementally up to 0.36 G. The maximum pore pressure generation we generated was 0.75% on shake 9. We first tested an untreated model, and the untreated model liquefied at 0.05 G. This was 40% relative density soil. So untreated 0.05 G following desaturation, 0.36 G, and it still hadn't liquefied. Came back the next day, spun it up again. We did 6 more shakes of 15 cycles from 0.34 to 0.44 G. That kind of maxed out the centrifuge. Then we did some additional shaking at that maximum acceleration of 30 cycles and 45 and stopped, and then 45 cycles. The upper sand liquefied in the first shake at 0.34 G. We're pretty sure that's because overnight the gas vented up through the soil and loosened the upper layer. But after that, we had no liquefaction for the additional shakes. The maximum pore pressure ratio that we generated, and by now the soil had densified a little bit, was 0.3 G. Was 0.3 pore pressure ratio. So this kind of tracks the saturation. This is treatment of the model off the arm at 1 G. Then if you do centrifuge testing, you know you got to put your model on the arm and balance it so that you don't get excess eccentricity, induced vibrations. Then we took it or left it on the arm at 1 G and did additional treatment, got the degree saturation down to about 90%. And then we did our first sequence of shaking. Notice that the degree of saturation continued to decrease during degree of shaking. Let it sit overnight and did the next set of shaking cycles. And here's the pore pressure generation. This is where the untreated model liquefied. You can see that, excuse me, 0.05. Yeah, this is where the untreated model liquefied. You can see the pore pressure ratio start to climb. In the upper layer, we had very loose, it was most significant. But so we got up to 0.7 G and then shut it down overnight, came back. And the next day we got liquefaction in the surface layer and relatively high pore pressures in the other layers on the first cycle. But then after that vented, it stayed pretty stable through the rest of the shaking. Pretty successful set of tests. There was some settlement, particularly after the soil liquefied. In prototype term, it would have been about a meter. And certainly that contributed to increased technical distance later on. And yeah, the total change in relative density to 155 millimeters of prototype settlement was about 10%. So by the 9th shake, we were up to about 65% relative density. Still relatively loose, very liquefiable soil. So taking 60 cycles at 0.35 G is pretty good, pretty substantial liquefaction resistance. All right, so centrifuge testing. What are our conclusions? Well, that MID, microbial induced desaturation without precipitation, may be effective for liquefaction mitigation. Have to caution this in that pore water viscosity issues limit this conclusion. Usually when you do centrifuge tests for liquefaction mitigation, you increase the viscosity of the pore water for modeling purposes to get the right rate of dissipation. We couldn't do that because that would have affected our treatment solution. So we had the viscosity of water, pore pressures were dissipating faster than they should have in the prototype. So that's a limitation of centrifuge testing. The associated settlements still needed to be considered. We did demonstrate that biogenic desaturation is possible under field stresses. And gas production, but there was this concern that gas production under low overburden may loosen soil. And we still hadn't addressed this issue of persistence. Persistence and the associated settlement were kind of the key issues that we thought we needed to focus on. Parallel to this, same student in the centrifuge testing conducted what we call a techno-economic assessment, comparing desaturation to the best available technology. And we created a scenario with a substation in the Port of Portland on 7.6 meters liquefiable soil, 12 meter by 24 meter footprint, 1.5 meter depth water table, had a clean sand with a relative density of 70%, And we compared MID, the cost of MID, to the cost of permeation grouting, which was, we thought, the best available technology for grouting under existing buildings. And because we're just, academic engineers, we enlisted Condon Johnson, local ground improvement contractor, to help us design the systems and cost the systems so that we could have some confidence that we designed a system properly and that we had good cost data. So on the left-hand side is the MID system, vertical wells, 3-meter spacing. On the bottom or on one side, we had injection wells, and on the top, we had extraction wells, so we were going to draw the substrates across the subgrade from one side to the other. And then the wells were screened at different depths. The permeation grouting, Condon Johnson decided that would be best with battered wells at 1.5-meter spacing. In fact, I think they had 2 wells at each grouting point, one that went in shallow and one that went in deeper. So battered wells, 1.5-meter spacing. The techno-economic assessment bounds. The bounds of your system are really important when you do a life sustainability analysis or a techno-economic assessment. So we consider treatment materials, well construction and installation, equipment mobilization, treatment deployment, the treatment products, including chemical and physical byproducts, and then well decommissioning and equipment demobilization. And here's the cost analysis. Bottom line, the project total for desaturation was 25% of the cost of permeation grouting. And remember, it was a very favorable case for permeation grouting. It was uniform, clean, granular soil, which, if you're going to do permeation grouting, you need relatively clean and open pores. So even if I have to retreat 3 times, I'm still going to be cheaper than going and doing permeation grouting. And retreating is no big deal. I'll just cap the wells and I'll leave them there. I'll monitor P wave velocities. If they decide it's increasing, I'll come back and retreat, just like our colleagues at Portland State are going to do at the site that we'll visit tomorrow morning. So from our techno-economic assessment, we concluded that MID significantly more economical than permeation grouting for remediation under existing buildings. It's also likely to be more widely applicable than permeation grouting because there's less pore size restrictions. Permeation grouting, you need open pores. MID, fine sands or low plasticity silts, we can penetrate the soil. Still, the efficacy of MIT needed some field studies to show that it would really work. So that brings us to the MID field testing, which we conducted in collaboration with Portland State, University of Texas, and DOGAMI, Oregon Division of Oil and Gas and Mineral Industries. I need to credit Yumi Wang for helping us locate and get set up on the sites we used and clear some of the hurdles for us. We had funding from NHERI, from my Center for Biomediated Bioinspired Geotechnics. We successfully desaturated 2 sites in Portland, and I'm going to stop there because I don't want to take any more of Diane's and Arash's thunder, but they'll tell you more about that. And then next up, starting in 2 weeks, actually, an industry partner of ours is going to apply this technique in Richmond, British Columbia, beneath some levees that protect Richmond from sea level rise, but are founded on liquefiable soil. So there are risks for liquefaction. Safety margin has been reduced by sea level rise, and we're going to have a pilot test where we use MID, actually MIDP, to mitigate liquefaction in Richmond. And so we're looking forward to that. So quick acknowledgement, most of this testing was based on work funded by the National Science Foundation at our Engineering Research Center. I need to say the opinions, findings, and conclusions of recommendations expressed in this material are those of the authors and do not necessarily reflect Major League Baseball. Oh, no, I'm sorry. NSF. And most of the testing and analysis presented here were done by 2 of my PhD students, Sean O'Donnell, who's now at Geosyntec, and Caitlin Hall, who's now at the University of Arizona, the second best university in Arizona, as part of their PhD research. All right, and that's my story, but I'd be happy to answer questions.
It does mitigate the, basically I can't remember the ammonium things.
Ammonium chloride?
The ammonium chloride byproducts.
Well, it's not a byproduct of MIDP.
Okay,
It's only a byproduct of MICP and EICP. And for that, to answer that question, you need to do fate and transport analysis. And I do have a new PhD student who's developing a fate and transport analysis. Because the question is, we know right away, you know, so one of the other techniques that we use for MICP is we create biocemented columns, like a soil cement column. So yeah, the ammonium's high in the column, but you know, what does it take? What's it going to be when it gets to a sensitive receptor? So we need fate and transport analysis for that. But that's really been a hindrance. When we tried to get some test sections of MICP, that question always comes up. What about the ammonium chloride byproduct? And that's deterred Menard and deterred Keller from investigating or investing in that technology right now. Anybody else?
So like, let's say we have a layered soil
Yep.
system here.
Yep.
And you have some sands, you got some silty sands, some silts in there. So I can imagine, maybe lower permeability might be a little harder to kind of flush the food through that. But do you also have the issues with like capping layers where like that nitrogen gets trapped underneath some of those? And
Yeah.
is that good? Is that bad?
So, I mean, that's why you need an engineer to design the system. It can be bad. So we've used these large plexiglass tanks to look at layered systems. And yeah, the gas can collect it as a lens underneath a capping layer. And in fact, it can then fracture that layer and vent in the tank. But in the tanks, we're working at 1 foot overburden pressure. In the ground at high overburden pressures, I don't think it's going to be that high, but it is an issue. So you don't want to go crazy and generate too much gas. Richmond, it is a layered system, so the injection wells are going to be screened at different elevations to match the layering. When you have lenses, it's a little more difficult. To a certain extent, the system is self-compensating because when you start to generate gas and desaturate the soil, the hydraulic conductivity goes down. The hydraulic conductivity of an unsaturated soil is much lower than that of a saturated soil. So that then pushes the treatment solution into the areas that have lower saturation. So there's a little bit of self-compensating there, but it's an issue, that has to be addressed with the treatment system.
Just as a follow-up, when you say like you vent in the case of
Mhm.
your all that gas is escaping, but like, does that cause your soil to resaturate, or is it just you lost excess gas?
Basically, it's excess gas because the gas in the pores stays in the pores due to capillarity and surface tension and all. But you create a vent or a fracture, and some of the gas vents through the fracture, but the gas in the pores, from what we've seen, stays within the soil. I think there was a question to that.
You mentioned in the centrifuge testing, you had quite a bit of settlement. Am I correct in understanding this approach? You went the liquefaction, but you're not kind of associated.
No, so if you looked at the results, until we got to really high levels of shaking, like for the first 7 or 8 shakes, there was little to no settlement. But so it depends how much you've treated the soil. If you've treated the soil to suppress pore pressure ratio, keep it down below 0.3, you're not going to have any settlement. If you start getting pore pressure ratios of 0.7 or more, then you will have settlement that you'll have to deal with. So the key is to have enough desaturation in the seismic environment. You don't have too much because you get venting and burping, but enough so that mitigates liquefaction, but you don't get pore pressures high enough that, and you don't get pore pressures high enough that would cause settlement or measurable settlement. Yeah.
So there's also all this testing is in sand, right? How does this work in silts?
Well, I'll let Diane and Arash answer that. the challenge in silts is the time to get the treatment solution into the soils. And there you're limited by hydraulic conductivity and by the fact that, yeah, when you desaturate it, the hydraulic conductivity gets even lower. So. Anybody else? No? All right. Thank you.
So I think we end up a little early, like based on our agenda, but like yeah, let's we'll have some like coffee break and then we will like meet again like 15 minutes earlier. So we have some question time for other presentations.
We have fun.
That's that.
We have fun.
Coffee's here yet.
Okay.
Can get a coffee good break without a coffee.
Okay, so all right, so